So let's start then with the notion of warm-up and muscle temperature. It seems to be that if we look at that set of information from Dave Bishop, it seems to be quite important in terms of a lot of the responses that we get. So we'll deal with some of these in turn. So let's think about these temperature-based responses. Well, if we look at the evidence, and this kind of set the scene, what we know is this: mild warming has been reported to reduce passive resistance of the human metacarpal joint by around 20%. So that's quite significant. That's not a significant raise in temperature, just mild warming. An increase in temperature has also been reported to decrease the stiffness of muscle fibers during contraction. So again, if fibers have less stiffness, then fundamentally what they're going to use is less energy to generate the same amount of force. If a fiber is stiffer, it's going to require greater cross-bridge interaction than a less stiff fibre. And the evidence seems to be quite clear that muscle contraction is a temperature-dependent process. We've also got evidence to suggest that performance changes following warm-up may result from increased oxygen delivery, which is what Dave Bishop was referring to. Why? Because of a rightward shift in the oxyhemoglobin dissociation curve and a vasodilation of muscle blood vessels. So there's two things that are wrapped up in that kind of paragraph there. The first is that we know that the process of oxyhemoglobin dissociation is temperature dependent. And there's very, very good evidence to show us, not even exercise science, but if you just look at human biology, that the release of oxygen is accelerated when we increase temperature, and it is decelerated when we decrease the temperature. We also know that the process of vasodilation is temperature dependent. So when we are raising core temperature, not necessarily through exercise, but it may just be through exposure to a higher atmospheric temperature, we are trying to dissipate heat. And one of the simple ways to dissipate heat is by moving the blood to the periphery, to the skin, to dissipate the heat. Well, we achieve that by creating a vasodilation to the skin, and we probably get a vasoconstriction to the deeper parts of the body, to the kind of the core region. So we know that is very much not a temperature dependent process. And if we take that a stage further and think about that in terms of exercise, you can suddenly understand actually why doing some form of warm-up potentially is beneficial. One, you're getting that release of oxygen, which have got oxygen being made more readily available, which is beneficial for the process of aerobic metabolism, oxidative phosphorylation. But secondly, we're getting that vasodilatory effect, which is reducing mean transit times. It's reducing the resistance to oxygen delivery. And so what we get is a more efficient process in terms of O2 delivery to the muscle cell. Now, if we look at our O2 hemoglobin curve here, we can see it quite neatly in terms of this image. So what we have on our x-axis, here we've got our partial pressure of O2, and here we've got the oxyhemoglobin saturation. And what you can see is what happens when we change the temperature. And this is changing blood temperature. So this is kind of the normal response. Okay, and then if we change the temperature, what you can see is if we raise the temperature, you release for the same pressure more oxygen. So if you look here, we've got kind of a normal temperature, normal blood temperature. So we've got full saturation. We're full saturation at around about partial pressure of say 100 millimeters of mercury, and we start to get a desaturation, quite significant desaturation of about 20% desaturation at around 60 millimeters of mercury. However, if we look at raising the temperature, now look what happens. Fundamentally, for the same pressure, we've got less oxygen on the cell, so we released more oxygen. Doesn't imply we've got more CO2, it just means we've got more oxygen being released. And when we reduce the temperature, for the same, if we take the same pressure, so let's say we take a partial pressure of 60 millimeters of mercury, you see here we've got about a 20% desaturation. Here we're probably in the region of about a 25% desaturation, and here where we've reduced the temperature we're in the region of around about a 5 to 8% desaturation. So it shows you quite compellingly that effect of temperature on the release of oxygen, and then you have to take that stage further and go, okay, that oxygen then becomes fundamentally important in metabolic processes. If we then carry on this conversation and then we look here in terms of changing muscle temperature on the force-velocity relationship and the power-velocity relationship. So if we take force-velocity to start with, so we're showing force here in torques, in Newton meters, and what we've got is a conventional relationship, which is that kind of concentric relationship, which is you've got a slow angular velocity, you get a high torque or high force output. And then as the velocity increases, the amount of force being produced decreases. But look at what the effect is when we go from a normal temperature, which is our solid line, to an increased temperature. So for the same angular velocity, you get greater force being produced. And so that's really beneficial. If you think about that in terms of sporting performance, in any sport, if I'm producing more force at the same angular velocity, then by definition, I am going to be generating more power. And we can see that in our power profiles. So this is our power profile, and remember that peak power doesn't occur at the highest angular velocity or doesn't occur at the highest torque. It's a function of both of those parameters together. And so what you see here is this is our power profile. So here's our peak power, and you can see that it's occurring at around about, it's difficult to be precise, but you can see here kind of our normal temperature here. It's occurring, if we assume this is 100% of torque, it's occurring at around about, let's call that 40% of the peak torque. And it's occurring at around about 50% in terms of 50 rads per second, as an example. If we then go for the normal for the raised temperature, one, you're producing more power because you are producing more torque for the same angular velocity. But notice now it's occurring at a much higher overall angular velocity, much higher angular velocity. And it's occurring, as we say, with a much higher overall torque profile. So it's really showing us the benefits of temperature on both force and power production. Not because they're oxygen dependent, but because, as that original slide was suggesting, there are clearly benefits here in terms of changing the characteristics in terms of the way the muscle operates in terms of force generation. Now, if we go a little bit further into this and we look at some quite old literature now, and this is something that will become apparent, that it is not a topic that receives a lot of attention in many ways, which is such a pity. So here we've got some data which is taken from the late 80s. And what they've had participants doing is they've had participants doing 20-second cycle tests. These are 2/3 really of a Wingate test. And what they've then recorded is we've got the peak force being produced over time, and then they've done this under a series of conditions. So they've got a kind of a normal muscle temperature, and then they have got a raised temperature at 44 degrees, and then they've got reduced temperatures. So here's our normal response in terms of the peak force that's being produced over the 20-second cycle period. But look what happens when they raise the temperature. They've raised muscle temperature. Now what you can see is they're producing a higher overall peak force. But actually what is quite fascinating about this is, in the end, they end up, not surprisingly, at a very similar minimal force over the 20-second time period, which tells us actually what they're showing is a greater rate of decline. And we'll perhaps come back to that later on, because that may not necessarily be quite as beneficial as one anticipated. When we look at the reduced temperatures, what you see with the reduced temperatures is clearly the peak force is lower, and the rates of decline are very similar to what we see in the normal rested kind of temperature. And then if we take that same data, what they've got here is pedaling rate, and they've got this against peak power. And again, what you see is when we raise the temperature of the muscle, the overall peak power increases, and it actually occurs at a higher pedaling rate compared to normal temperature. And when we come down to the lower temperatures, the pedaling rate and the amount of power being produced are significantly reduced. Excuse me.